Hi all, welcome back. Today we are starting to new series related to the spacecraft attitude determination and control system. In short, it's called the ADCS. So this series is going to helpful for those who are working in the spacecraft space sector, especially for GNC guidance navigation control for spacecraft system. So how we control the satellite. So spacecraft means satellite, right? So we will try to understand that. So let us start. So ADCS, this is a short form, attitude determination and control system, right? So first we should know what is the attitude current now, and then we apply the control, right? So I think this series is going to helpful. So this is a called the guidance navigation control. Sometimes this also written the NGC. So means navigation, first we know where we are, right? Then we have based on the guidance definition apply the control to get the our desired attitude. So we'll let you know what is the attitude. We will understand this lecture the fundamental terminology and all aspects which are necessary for coming lectures. Yeah. So what's the first lecture? What we are trying to learn in this lecture. So what is the spacecraft attitude? What is the ADCS? And why is the attitude control required? And what is the orbit versus attitude? And what is the main ADCS components? And what are the attitude sensors, what the attitude determination, and spacecraft actuators, closed loop ADCS architecture, typical operation modes. We will give briefly touch all these points and aspects, and of course this in our coming lecture we will go in more deep. Yeah. So develop the complete physical picture of spacecraft ADCS before introducing deep in mathematical models, right? Yeah. So what is a spacecraft attitude? So attitude is nothing but this is spacecraft describe the orientation in space related to the chosen reference frame. This is important. So let us say this is our body, this is a 3D body, sorry, this is a rigid body, okay, and in 3D space, okay, let us say we are just presenting the x, y and z, okay. So how with respect to the reference frame, let us say this is a reference frame, and how much altitude is there, how much orientation is there, right? So this is important. So we need to understand that. So in our 3D space, 3D we require two orientation, right? So this is a angle quantity, basically angular quantity. So when we talk about angular quantity means basically here we deal with the rotational motion. So in case of ADCS, here we focus on the rotational dynamics, right? So here rotational like torque, right? Torque come into picture, right? Movement come into picture like that. Hope you understood. So here is a spacecraft plus x axis pointing. So we need to point, right? So let us say this is our and this is our the spacecraft, right? And this is our x axis. Let us say we are zooming. So generally towards the x axis, towards the our, let us say this is a orbit, this is Earth. So toward the x, toward the Earth, generally we consider the x. So we will discuss. Okay, we will understand that all aspects So there is a by plus by axis pointing, and of course this is just perpendicular to the x and by. So physical interpretation, but the physical significance here. Attitude answers how the spacecraft oriented. It does not tell us where the spacecraft is located. So make sure that attitude is not equal to the position. Okay, position is a linear quantity. So in this deal with the translational motion. Attitude deal with the rotational motion, associated with the rotational motions. Okay. Yeah. So position versus attitude. So what is a position? Let us say like we have x direction moment and y and z. So there is a spacecraft. So this associated mainly the translational or orbital motion. So in case of orbital motion, generally we deal with the translational motion, right? In attitude, generally we deal with your rotational motion. So we deal with the orientation using like psi theta phi, phi theta psi, right? Or the quaternion base. Okay, so this is a way to present the attitude quaternion base. So we will discuss later. So where it is pointing, right? So there are different methods. So we can present the attitude. I mean, what is called orientation, right? So position attitude fundamentally different states. Okay, so this is associated with the linear or translation motion, and this associated with the rotation motion. Of course, this is here. So basically in 3D, why we needed actually or attitude, because position is not sufficient, right? Because in 3D position is not enough, because it's a moving body 3D, so we require to orientation. So the orientation details also required. So this is a 3 parameter is position, 3 parameter is attitude, right? So this is a 6 parameter, right? 3 is a linear, 3 is a rotational associated with the attitude, right? So it means for understanding the 3D rigid body in 3D, we require at least 6. Then only we can tell them the position, right? Where it's right now. Okay. So yeah, so translation and rotation. So space has two fundamental different types of rigid body motion. Okay, generally we deal with the rigid body spacecraft. Yeah, some flexing is also there because of the solar panel. We will discuss all in detail when we go further. Yeah, so translation motion. This is a vector position vector R. Okay, x by and z transpose, right? Or xb can also write in the column vector also. No worries. And this is velocity. So all each axis, right? X, y, and z, right? So this is orbital or translation motion. So orbital motion is associated with the translation motion, and attitude motion associated with the rotational motion. All right. So orientation phi theta psi, angular velocity omega x, omega y, omega z, right? So yeah, so here 6 degree of freedom. So pre-moving like pre-moving spacecraft, right? So this is at the moment of the 6 independent direction motion there. Okay, so the number of the axis direction, right? 3 rotational and 3 translational. All right. So x by z translation roll pitch या जल्दी rotational जल्दी we deal with the roll pitch या right. We will discuss okay what is a roll pitch. Just now you for sake you understand that this is motion, rotational motion for the each axis x y z axis, right. We will discuss what is a mean roll and pitch. Okay, all right. So ADCS mainly deal with the spacecraft 3 rotational degree of freedom. Okay, so we have to restrict with the ADCS motion with the deal with the rotational motion, right. And we have to bother about the 3 axis rotations or orientations, right. Roll, pitch and yeah. All right. So why does a spacecraft orientation matters? That's very important because we should know what is necessary. Why we study this actually. So spacecraft may carry solar panels, be required to powers, powers for the spacecraft, right? So because of battery for to be charged, right? So we require solar panels, right? Communication at instance also. So for this orientation to be needed towards the sun pointing, right? So that it will be start to give some power, right. Communication antennas, earth observation cameras, and star trackers, scientific payloads. Scientific payloads it is necessary to like based on the like earth observation, so it's towards to the earth, so orientation correction needed, docking interfaces we will discuss later. Like this is a also one complex application nowadays evolving, and most of the we have working on this part. Yeah, pointing requirements, different components must point toward specific directions, like solar array towards the sun, antenna toward the earth, then only communication to be established, right. Camera target to be target, docking port of course like target vehicle we want towards to pointing, right. Yeah. So in the incorrect attitude may result in loss of power. This is very important because if you is not pointing to sun, so it will be it will not be point to sun, right. It will not be charge the battery, and consequently will not able to proceed further testing or and all, right. And communication, observations, capabilities, and mission performance. Yeah. So these are the like problems may occur, poses problem because attitude correction, right. So you understand how much important there. So like example earth observation spacecraft. So there are various applications. So in earth observations satellite must orient its payload camera toward the required target on earth. Yeah, so the target direction and then the desired attitude we want, and then the spacecraft intends to rotate and achieve this intended attitude, right. So conceptual control problem, a spacecraft has the desired attitude and initial actual attitude, okay, present, and we have to achieve this one, right. So attitude ADCS system attempts to minimize the difference between them, that's all. Okay, we want to minimize that error. Let us say this is a initial 30, we want to 60. Okay, so 30-degree correction there we have to correct it. So attitude error is not generally computed by the symbol subtraction. So this is very important. Like let us say like position there, let us say 2 meter, and we want to 5 meter. So we just simply do subtraction, right? But here we will not do subtraction. Okay, here we will do some other way to apply there. So we will use rotational matrices and quaternions, right. This is a way to apply, and methods are there to apply that to find out the attitude error, right. Yeah, so communication satellite, like communication spacecraft may need to maintain antenna pointing toward earth, solar array pointing toward the sun, right. Payload orientation within the specified pointing accuracy, right. So what is my current orientation? So this is attitude determination problem. So in this we go for the navigation, right? Sometimes we also call the, like we are estimating, right, from this determination. So, yeah, and so this all part in the deal in the navigation, right? So how should I rotate? How should I rotate? So this is attitude control problem, right? So attitude determination control system. So ADCS is a spacecraft system responsible for determining the space orientation. We know the and estimating the rotational states, yeah, and computing required control action. So this is a here actuator to be involved, right? Yeah, free section. We will discuss later what's the means to provide this, and generating physical control torque, yeah, and maintaining or changing the spacecraft attitude. So this is very important. We have to maintain it or we are changing. So this we have to sense it through the sensor. So this will deal with the navigation part, and we have to estimate because a lot of noisy data there, and then decide it and take a action actuator part, hardware part. So attitude cell letter, desired attitude letter is a QD and actual is Q, and attitude error we can find out this way. Okay. So we will discuss later why we are doing like that. So let us say we have to achieve 30 degree, right? 30, right, and we have to 60. So generally we in linear we just subtract it. Algebraic summation is algebraic of substitution is sufficient for this, but here is not sufficient. We go for the inverse. So it means that we have to go for 30 minus, right? This is minus actually. So let us say this is code 30, okay, and this is 66. Inverse means minus 60, right? So it will be, we get negative 30. So this will be basically we want to achieve it. We'll discuss later in detail. So control objective, the drive attitude error toward identity, yeah, and angular velocity towards the reference. So this is very important. So ideally it should be go for the identity, yeah. Yeah, and omega is to achieve the our desired velocity. So quadrant mathematics will develop later. This is not a problem. Yeah. So compare ADCS closed loop architecture like desired attitude controller we put here, and finally actuators and specific dynamics, and this is attitude sensors, right? And then we go for the estimation algorithms, right? And then we go for the attitude controller, yeah, right? So sense, then estimate, then controller, then actuator. So attitude sensor, typical sensor like sun sensor, magnetometers, star trackers, gyro knife, IMU, and earth horizon sensor, because here some sensor is needed, right? So purpose, sensor provide information about spacecraft orientation, because without knowing the orientation, how we bird we correct it. And reference direction also is important, okay, and angular velocity, and yeah, rotational motion data to be needed for this. And real sensor measurements contain noise, bias, drift, and errors. There are a lot of problems coming in the real sensor, so we have to correct this also, yeah, nullify it to some extent. So noise, bias, drift, and errors. So attitude determination, sensors objects such as star vector and plus sun vector, right? So as proceed through attitude determination algorithm to obtain the Q estimate. This is like we are estimating one state actually, right? For actual thing is Q, but we are estimating, right? So there are different methods over there. Typically method like triad, and then port Q method, Q is Kalman filter, extended Kalman filter. We will discuss in detail. Yeah. So estimated space orientation and depending on the estimate other states such as gyro wise, right? So actuator controller. So just now we know we can find out the actuator like that. Okay. Angular rate error omega is equal to E is equal to omega minus omega d, and controller computes the DC function of the error, right? And we possibly we design the control like sometime we design simple control PID, QR, quaternion feedback controller, sliding mode controller, yeah, MPC model protected controller. Yeah, so spacecraft actuators. So controller calculates the required torque, but a physical device must generate it controller to command actuator and torque, right? So internal momentum exchanges, reaction wheels, and control moment gyros, and external torque generation like magnetorquers and thrusters. So this is already internal moment exchanges, right? So actuator convert control commands into physical spacecraft rotation. So there are different methods like how we can achieve it, how we can correct the attitude. So these are the internal movement exchanges we are doing here, and this is the external torque we are providing here. So this is like based on the high command we require, go for the external torque. Reaction wheel basic idea. So reaction wheel is mounted internally in the spacecraft. When the wheels accelerating zero, means the rate of change velocity zero. So it exchanges angular moment with the spacecraft. Okay. So angular momentum will be constant or conserved, right? So this is spacecraft angular momentum. This is a wheel, so it will be constant. So for negligible external count, if there is no external torque, so it will be zero, right? So we have to apply this one actually. So if the wheels gains angular momentum in the direction, so delta S wheel, so spacecraft gains angular momentum in the opposite direction, right? So this is very important because it's zero, so we have to find this one, so it will go to negative direction, right? So magnetorquer basic idea. Magnetorquer produces magnetic dipole moment M, and Earth provides local magnetic field B, and resulting control torque is tau is equal to M cross B, right? This is dipole. Advantage is like simple, lightweight, and no propellant required because thruster propellant will be saved, work will be saved, common in the quiz sets. So like there are various classification of the spacecraft also in terms of size. So limitation, torque perpendicular to B, so instantaneous torque is not independently available in the every direction. So this is very very important. It's not available because this is perpendicular, so it will not be correct to our other direction. Yeah, so major disturbances like external disturbance torque like gravity gradient torque, aerodynamic drag torque, solar radiation pressure, residual magnetic torque, internal disturbance torque. So these are the disturbances to be associated with the spacecraft to cause always create a problem to so contours correction to be required for orientation. So rotational dynamics of a spacecraft respond to both control and disturbance torque, right? So this is the I omega, this is inertia. So this will be our disturbance, and this is our the control. Okay, and this is our the omega cross I omega. Okay, tau is constant, tau disturbance torque. Yeah, let us understand that what's the things there. So this is a main core rotational equation I omega dot. So spacecraft inertia tensor, omega angular velocity, and tau applied torque, right? So this is a fundamental nonlinear rotation dynamics equation used throughout the spacecraft attitude control. Okay, so we will discuss this also. This is a speed, angular speed. I will discuss this what is happening actually later. So what does ADCS actually control? ADCS may regulate or track spacecraft altitude Q, right? We know, and of course for altitude, so we require to also know the velocity also omega, and pointing error, slew trajectory, nothing but this is the history of the position, velocity and acceleration. We'll discuss later. And direction wheel momentum we should know. So two main objectives: attitude regulation and attitude tracking. It is very important because over here regulation, like we have the fixed value and we have to regulate it actually. Achieve, that's all. And here is over time is our reference point going to change, so we have to track it over time, right? So that's the point actually. So here reference is not fixed, here reference is fixed. So objective depends on the mission operating mode. So various mission operation mode which is going to change, right? Yeah. So attitude regulation, attitude tracking. So yeah, already I discussed you. Attitude regulation means maintain the fixed desired attitude, right? So here we are fixing QD. So this is a earth pointing and sun pointing safe mode. Okay, safe mode orientation. But of course, attitude tracking means here is a command is also a function of the time. So you're changing over time our let us say like sin omega t. So sin function, yeah, some other function, it's changing, right, over time. So we have to track it over time, right? We have to correct over time. So that's the things there. For example, like target tracking, we want image maneuver. We'll discuss what is maneuvering and rendezvous and docking, right? So this thing also we discuss. Okay. Yeah. So here, like typical ADCS operation modes, this is very important, right, to understand the spacecraft modes. So spacecraft may use different sensors, actuators, estimators, controllers in different mission phases, like detumbling, sun acquisition, course pointing, fine pointing, slew maneuver, momentum dumping, safe mode. So important ADCS is used in a mode-based system, not one control running identically throughout the mission. So this is very important. Based on the mode base, control to be changed, to be transition right, so that stability should be maintained, and based on the mode, our we achieve our requirements, right? Yeah. So examples, mission sequence like launch vehicle suppression, then we start detumbling, then we go for the sun acquisition, then we go for nominal altitude control, then mission pointing or tracking. So typical progression after suppression, the spacecraft first reduces excessive angular rate. This is very important, and establishes this safe altitude, and then transition to the mission operations. Okay, because this is very important. Otherwise, will not able to because tumbling is starting, right? So we have to detumble first. Yeah. So ADCS is a feedback control system. Yeah. So here we constantly using the feedback so that we should know where we are. So desired attitude QD and estimate attitude Q cap, and attitude error is Q is equal to QD, and we put the cross product here and this one, and controller produces QE with the torque actually, and actuator produces the torque to spacecraft rotation. Sensor then measure the new state. So this is feedback, we will discuss later. So this error, and we put the controller, and accordingly torque will be based on the what the needed torque to applied for the actuator, so that our attitude to be corrected, right? Yeah. So again, like reference attitude and attitude error, controller, actuator, spatial dynamics, sensor, estimator. So reference, then error, controller, and actuation, dynamics, and measurement. Yeah. So these are the sub components we need to understand that. Yeah. So important question, like we will study like quaternion, attitude quaternion, angular velocity, inertia tensor, angular momentum, torque, rotation matrix. Yeah. So all those parameters, associated with the rotational dynamics and kinematics part. Yeah. So attitude representation, like kinematics. Yeah. Dynamics and control. We discuss what the dynamics, kinematics. So the big picture, like you think about it. So reference frame, rotational mathematics, go for attitude kinematics, then go for rigid body kinematics, then space car environment and disturbance we have to think study about. So these factors to be considered in the analysis, sensors and attitude determination, control algorithms, actuators, mission level ADCS. So complete progression for attitude mathematics to mission level control, right? Yeah. So keep what we understood till now, like attitude describe spacecraft orientation, right? And position attitude are different physical quantities. ADCS determines and controls spacecraft orientation. Sensor provide information about rotational state. Estimator construct spacecraft attitude. Controllers calculate required torque. Actuators physically rotate the spacecraft. Disturbance continuously affect attitude. So co-radial actions estimate and control and action, right? Yeah. So next lecture we'll discuss about like inertial reference frame and Earth center inertial Earth center, Earth fixed orbital, yeah, and spacecraft body frame, sensor frame, vector representation, transformation between frames, yeah. So why this matter? Before describing spacecraft orientation, we must first answer like orientation related to what. So we have to want reference, right? Then only we subtend the angle, right? So hope I think we understood. I think this is the first lecture. We just try to highlight the highlights of the fundamentals of ADCS and what's terminology we need to understand and deep down much more. So that's we just highlighted. Hope you get some idea. Yeah. Something you doubt, please comments so that we will clear those doubts. Yeah. So that's all from this video. Yeah. Bye bye.